Hello everybody and welcome to this run through of Rust by example. Embarrassingly, you just heard me giggle on stream, but hopefully everything will be fine. If you are joining me live, feel free to introduce yourself in the comments and ask anything as we're going along. If you are listening to the recording, then please subscribe in whatever channel, whichever way you would prefer. And you can be updated with future content. Okay, so what are we going to do? We are going to look through all 23 chapters of Rust in Action. Sorry, of Rust by example. Rust in Action is my book. And what is Rust in Action? Well, Rust in Action, sorry, what is Rust by example? Rust by example is a website that has runnable code examples that takes you through almost the entire Rust language. So you can kind of give it a taste before you actually try it yourself. And what I want to do here is show you that you can run Rust. So we've got hello world there, and I'm going to say, hello internet. We can run it again and we get an output. And so we have got an activity. So let's go through some of the text. This is a comment, it's ignored. The code is editable, feel free to hack it. And you can always get to the original by clicking reset. If you have watched no more than this content, that's all that you need to go and do it yourself. But what I really want to do in the next couple of hours, hopefully no more than 4, otherwise I'm going to really sweat, is teach you as much as I can about the language in that time, and also show you that Rust is learnable. Rust is definitely something that you can pick up. And if you're excited about it, or even if you're interested, it's definitely not impossible. A lot of people say that Rust is like a really hard thing to learn, and I want to kind of challenge that assumption. And so let's walk through the code. We've got main. This is where all of our this is where our program lives. And we can, it says statements here are executed when the compiled binary is called. That is any code that's inside main. In fact, main is the entry point, and it obviously can call other bits of code. We've got a function here, hello world. It turns out though that this looks a little bit like a function, but it's actually a macro. A macro is a code that generates code, which sounds a bit stupid, but the reason why this is a macro is that it accepts multiple arguments. So I've got a counter next to me, and it says that there are 29 people watching, and the braces here get replaced. And in order for that kind of functionality to happen, we need some compile time code inspection of like what's actually happening, because integers are not strings, and Rust really cares about the data type. Oh, and so you'll find macros in places where you need to be very flexible. This enables the compiler to actually sort of provide some extra tricks, and printing to the screen with multiple data types is one of those tricks. Okay. We've got an activity. Click the run above to see the expect. Next, add a new line with a second print line macro so that the output shows this. And I'm just going to click reset again. And the next line is, hello world, I'm a Rustacean. So as soon as you execute this yourself, you essentially get to say that you have compiled Rust code and you are a Rustation. So well done. Congratulations to you. I really hope that you are going to have a lot of fun in your learning journey. I'm just going to check the comments, and it is really lovely to see that there's a lot of discussion happening, and one of the important ones is this one. If it's a speed run, where is the timer? I've got a timer. I'm currently at 6 minutes and 54 seconds. And so I'm going to try to kind of hold things in. Maybe I should have like had an actual animated clock. I didn't get quite that far. Hopefully you'll forgive me. I've got 23 chapters to get through. In fact, 22 now. I've done one. And 4 hours is 60 times 4 is 240 minutes. And so hopefully there's about 10 minutes per chapter if I've got my mathematics right. And so I'm budgeting about 10 minutes per file. And okay, any program that requires comments, Rust supports a few different varieties. So I'm reading the comments off stream and trying to think of, like, should I bring things up? And I'm like, actually, no, I should actually focus on the book. So we're going to talk about comments in Rust. So these are sort of examples to, this is documentation for people that are reading the source code, as well as documentation for people that are for users of the thing that you are creating yourself. It says here there are multiple different variants, and you can create like a block comment or a single line comment. Interestingly, I've actually never thought of the block comments as block comments. I have thought of them almost always as inline. So if I wanted to comment out sort of a single expression, then I can just add the slash star and star slash. I've never really thought of them as multi-line functionality. The other variant is that when you see the bang or exclamation mark, this is a comment for the item that is following the sorry, it is commenting the actual thing that you are documenting versus a comment without a bang or a slash is generating a comment relating to the thing that follows it. This makes more sense once you start thinking about modules, but for now we can think of creating documentation with 3 slashes. Has to come at the start of a file, and for the main, it's like, this is my program. Your Rust doc will actually create an HTML page with an annotation around main that describes, that includes the text here. This is valid markdown, and so if we wanted, we can include a lot of other stuff in here as well. I could have source code, and so forth. But there's actually a whole bunch more to kind of dig into. And then let's move on. Formatted print. So we're talking about really elementary stuff, not because we want, because it's really important when you are starting out with Rust to be able to create little command line utilities and things that are made for your own use. And therefore we are going to look into this print line macro and several other variants that are really useful. Let's just try the code. We've got a whole bunch of stuff here. In general, these curly braces will be replaced or substituted by whatever variable in the position that it will face. Sorry, this is the 0th argument, and essentially to the format string, and the curly braces will be replaced. If we had 2 here, then the substitution would work in multiple places. You can also be more explicit with integer references, and this becomes more important when you want to go and reference the same variable multiple times. So we're talking about Alice and Bob here. We might change this to anything we want. And there is also the possibility to provide named arguments. I wonder if we'll get there. There is an update to Rust which might not have been updated into this example, whereby this named argument syntax can actually be expanded. So I've got subject, verb, and object, and I'm just going to very, very quickly teach you how to assign a variable. We do this with the let keyword, and I'm going to cheat a little bit by going off script. So one of the tendencies that I have is to go off script relatively frequently. So I'm doing myself I'm trying to stick to the time, but what I really care about is teaching. And so you'll find yourself using this new variable substitution method as well in recent versions of Rust. And you also have multiple different ways of formatting integers. So for example, we've got 69,420. It has a binary form, which is its 0s and 1s, an octal form, in fact, there are 2 forms of hexadecimal. One is lowercase and one is uppercase, and that is denoted by the small x and large x. The x stands for hex. And we can also use add a justification inside our numbers when we're formatting integers, so we can pad with spaces. And you are... Oh, I just by the way, I noticed, do I have a Discord channel? Yes, I do. If you go into my YouTube channel itself, which is youtube.com/timclicks, one of the links is actually into my Discord server. Green input, F strings into Rust. Yeah, essentially, one of the cool things about Rust as a language is that it was late. And so there were lots of really wonderful features in other language communities that we were able to like pull in from other places. And so Rust to me feels like a language that has been able to benefit from decades of experimentation and practical use of software and really accelerate people's productivity by combining all of these wonderful features. So I think of Rust as a functional language in disguise, but other people think of Rust in a completely different way. They think it's purely about systems programming. I'm slightly different. I don't think that systems programming is such a huge deal. And but yeah, there is another related question, which is, do I think that I want to get to? And I was going to say I wanted to deal with this later. I should think it, but I don't want to pull this up. That's incorrect. C++ uses snake case. It's like there was no other like systems programming language essentially, and C. They both use snake case. So there's much more to it than the affinity between Python and Rust. I think the real attraction to Python users. I was a Python programmer for about a decade before I learned Rust, and one of the reasons that I was attracted to the language is that it was sufficiently a sufficient improvement to justify a new language. Think about that. I experimented with Go, but I still found myself with null pointer references, with not understanding interfaces very well. But with Rust, I have no null pointers. Null pointers do not exist in the language. I don't have any problems with data being in the wrong place, and it protects me from other problems because I was always told that if you want to write native extensions for Python in C or in C++, that you should leave that to the experts. And with Rust, you don't need to be so worried. The reason I learned Rust was because Rust provides safeguards. It gives you control. It gives you freedom because it protects you from some really horrendous errors that are otherwise impossible. Okay, I should continue to talk about integers and printing them out. Rust even checks that my name is correct. So add the missing argument. Actually, let's just run this and just see. We haven't encountered a compile error yet. So let's do that. So I'll push play, and then right down the bottom, I get an error saying there's a propositional error. We've asked for a 1, but we don't have a 1. I'm sorry, this is a bit small. I might try and increase it. And so I asked for a 1. We don't have one. So what should we do? We need to go back to the code with James Bond. If I can find it, it's up here. And I need to add in, so I've got Bond, but I don't have James. So now if I recompile, I'm adding Control S because intuitively that's what my muscle memory does. Aha, and now we have a real program. We've got my name is Bond, James Bond. And these are all the formatting things that we saw earlier. Let's fix, so we've done that. Only types that implement display can be formatted with our little braces. User-defined types do not implement display by default. So one of the things that we haven't talked about yet, we've only learned a tiny, tiny fraction of Rust in our first 20 minutes. And we haven't talked at all about traits or interfaces. A trait can be thought of as like an abstract base class or an interface if you've used Java or C#. Now, or if you're, and so this format display thing is the way that it is saying that your I've got a struct here which is called structure. Let's call it something else. Let's call it stream, and we've got the number of viewers here, and we call it live stream just for fun. Now we want to be able to disable this will just not compile because so if I uncomment this line, it's saying that it's not going to work. And so it's just demonstrating that this is a problem. We'll talk about implementing traits in a little bit further on, but this is just a guidance to say that your user-defined types don't work by default, but we can fix that soon. This will not compile because structure doesn't. Okay, we've seen that several times now. Print line. Oh, For Rust 158 and above, you can directly capture the argument from... Ah, okay, so this is actually what I started with, or I said before, which is up here, that we can actually capture the named argument syntax. Okay, so Rust by example was right, and now we also get we get some more documentation talking about debug and display and how to implement them. So activities, fix the issue. We've done that. Uncommenting the line. We've done that. Add a print line macro that prints pi is roughly 3142, controlling the number of decimal places. Ah, okay. Let's do that. Uh-oh. I'm already late. Hopefully you don't mind. Is a struct similar to structs in C? Yes, extremely similar. They're Rust to assembly language looks exactly the same as C. Now, we were told that we should what we want is to print out the short form, but we have the long form. So I think the way that we do this is by saying dot and then with 3 significant figures. Aha! Hooray! I would be quite embarrassed. There will be times where I get stuck in this. I'm doing it live. This is not a recorded, like pre-recorded session. There is no cheating. And so there will be instances where I get this wrong. Okay, so now we're going to be talking about a trait in more detail. The print line macro that we just worked with was invoking the display trait. Now, debug is a simpler trait because it is designed for programmers, the people debugging their own code. And so it's slightly, well, it is less general purpose than your than the general display trait. Okay, all types that want to use standard format, which is the print line macros, require an implementation to be printable. So that is, you need to be able to know how to convert yourself to a string if you want to be formatted for the console. Automatic implementations are provided for types such as those which are in the standard library. All others must be manually implemented somehow. And we're going to show you 2 things. One is that by default, you can't print a type to the string because it doesn't implement format display or format debug. However, Rust does know how to automatically implement this trait for your type. So we've got a struct here, which is debug printable, okay, and it has a single integer inside it. Now, Rust knows how to print integers to the screen, and it actually can figure out how to print a structure that includes a single field that it already knows. So you can have this derive annotation, which will automatically write some code on your behalf. You remember how print line is a macro? You can think of derive as another type of macro. You decorate your function or your item, such as a struct, and Rust will build the code that you would have otherwise written yourself. Okay, all standard library types are automatically printable with what this the colon question mark. Now, what is colon question mark? We haven't seen it before, and let me talk you through. we derive the format debug, the implementation structure. Structure is a structure which contains a single I32. Okay, so we've just talked. It's the same thing here. Let's bring debug printable into debug printable, and we can also put structure into another. We could put debug printable into a thing called deep, and so because debug printable implements derive, implements debug. Deep can also implement debug. And now we have a new, I'm just going to comment all of this out and just talk a little bit about what we've enabled. So we've created a new, We've created a new type called debug printable with an integer inside it. And debug printable is now printable. Yay! But you notice that it exposes all internal details. We don't have any customization available to us because we're just relying on the automatically derived implementation. The integers themselves will implement debug, which we've seen with our field up the top on line 3. We've got Christian Slater as an actor, and these strings, which we formally call as string slices, are also able to be invoked with the debug trait. This will also print out the double quotes versus just providing asking for the display version without the colon will omit the quotes. And just to verify that it's possible to derive things whereby the internal fields are also derived, let's look at what happens with our second structure here. Deep debug printable will now print as well. Format debug definitely makes this printable, but does sacrifice some elegance. Rust also provides pretty printing. Okay. So, gosh, we're going to introduce some really nasty syntax very, very early on. We've got derive debug, which is what we've already seen, and a different form of struct that includes something that looks slightly horrendous. A lifetime parameter, which says that this person thing must live as long as the name does. So the name is a reference to some span of bytes that is UTF-8 encoded. That's what lowercase str means. And and the ampersand means that in local scope, we hold some reference to data. Now, the lifetime parameter isn't actually required in recent versions of Rust. Let's actually find out. I would really prefer not to scare people. Okay. So we do require a missing lifetime parameter. Whenever you have a reference inside a struct, Rust becomes very confused. Wow. No, it wants you to be very explicit with what you mean. And we want our person to live at least as long as the data that it is referring to. The okay. Let's see if I've got person Peter. Peter's 27, and we eventually will get to this variant here. But I did need to explain what on earth Peter was doing. Sorry, what on earth this syntax was. These names can be anything you want. We could, but by convention, they are just given single letter names, often just A. It's slightly unfortunate, but it's saying that that person must live as the person variable. Oh, sorry, the person data must live as long as everything that it refers to. Now, you can see here they've got nice white space, so it's nice and readable. If I omit the hash, or the pound sign, I think is what Americans call it, and run print, everything we printed out on one line. If I put in the hash, then I get the white space. If you, again, and this comment here is one can menu implement display to control the output. So the format display gives you complete control over exactly how you want things to be implemented. So does debug strictly, except that debug will it's semantically different, even though like the intent is different, even though what it ends up doing is just converting your type into a string, but for a different way. Aha! So now let's talk about display. How are we doing for time? We are kind of there, kind of on par. We're not really. And the format display hardly looks compact and clean, so it's often advantageous to customize the output. This is done by manually implementing format display, which implements these curly braces print markers. Variable substitution might be another way to do it. Implementing it looks like this. Now, what on earth? Now, what does it look like? Huh? Let's what it looks like. Allow me to just delete a whole bunch of stuff. I'll run this maybe. Oh, what have I done? My computer is freezing, which isn't useful. Oh gosh. I'm glitching in the matrix. Ah, it's trying to print. I'm a little bit worried. Have I not even got past hello world? Oh god. Format display. Okay, we're back at display. That's useful. Now, I want to run this code block. And I'm immediately out. Oh, okay, right. So there's no main function in here. So it got a bit confused with what I was trying to do. Okay, right. So one of the limitations of Rust by example apparently is that when it's, well, actually MD book, the software that is rendering the HTML, is that when there is a code block sample that doesn't have a main function, it doesn't seem like you can actually go and edit things as easily. Okay. Gosh. So we're talking about a trait here called display, and we want to be able to implement format display for our structure, which we've defined earlier up. Now, format display has one required method, FMT, short for format. And all it asks you to do is to write to this formatter object. The formatter is some relatively opaque type that you don't often need to go and inspect internally, because you can typically just invoke another macro, write, which takes as an argument a formatter or something that is able to be written to with the same syntax. So we could change this to, say, for example, we wanted to say whatever we wanted, we could put into that format string and it would, quote, just work. Okay. Format display may be cleaner than format debug, but it presents a problem for the standard library. How should ambiguous types be displayed? For example, if the standard library implemented a single style for all of vec_t, so vec_t is essentially a list, it's a shorthand for vector of some type t, what style should it be? Should it be either of this two? Ah, there is main. You can find it by pressing the eyes. I. Oh, I wonder why that one is hidden though. I can't, that's not editable. Not editable. Anyway. So, apologies for that. Okay, would it be either of these two? That is, should we have a colon delimited list or a comma delimited list? No, and it says, well, actually, there is no perfect way to provide a generic implementation of display for any arbitrary list of any arbitrary type. Instead, you need to describe to Rust how to implement display for your vector. And in this case, we've got min and a max, which is the we've got our format macro again, and we have self that we can delete self.0, self.1, and debug will be derived. So it's slightly annoying because we're talking about vectors. Oh, it's just essentially saying that there's no generic type, but so for your own, but we will find a way to implement this for ourselves. Let's print all of this out. And I want to add an extra activity in here, which is, okay, so how would I implement, let's say that I want a list of points. Here's a point 2D. And can I implement format display for a vector of points? Like, how would I do that? And I've got display here. And I'm going to introduce for loops, and I want to first write out a square bracket. So I'm going to create something that looks a lot like JSON. And this question mark syntax will return the result. There is actually, I think, a join method that I could invoke, but I'm just going to do this very, very briefly. For item, 4 point in self editor. Question mark, sorry, comma space. We don't want this in the very end, but I won't worry about that too much right now. And here's my point. Here are my point. Oh, here's my single point, and just create 3 of them. So we should be able to just print out. I also need to teach you how to actually create a vector. Now, there are multiple ways to create a vector because it's such a ubiquitous type, but it also includes, the standard library provides a macro that takes a list that you've defined and will automatically wrap that in a vector. So hopefully I've done the right thing. No, I haven't. Vec is not defined for the current crate. Only implement. Aha! The I've forgotten about the I have forgotten about the orphan rule. Now, it turns out that you can't implement foreign traits for foreign types, and Rust won't allow you to do this. And so I'm going to have to pause there and carry on with the book. Otherwise, I get this problem. So Andre here has done and like pointed out that like this can't actually happen. We need to define our own custom container that wraps Vic. Now I really should carry on. But I kind of can't help myself. So if I wanted to be able to create a container, I now need, so I've got my points in a vector, and that has an inner. Now this seems like a very cumbersome way to go and create a printable thing. Oh gosh. Oh, okay. So one of the problems that this one here, at the end of this call, I add a semicolon. The result of a semicolon is this thing called a unit type. Now I've got two options. One is I could just return the result that the last write provides, or I can wrap okay. But I think so. I think I'll do this. Just return the result of the last write. If you are brand new to Rust and you don't know what on earth I just said, please pause. Please just bear with me. All I wanted to do was to get my was to get my points out. And so I have been able to do that, and now I'm going to be able to rest in peace, or just kind of like sleep a little bit easier knowing that I was able to figure that out. And so here are our 3 points inside a list, and just with the comment that we can't implement foreign traits. And so this code that we're writing right now is distinct from standard format display and vector. And because the trait lives elsewhere and the vector type lives elsewhere, we need to one of the things about the way that the traits are implemented is that Rust will prohibit your ability to go and implement some trait for some type that you don't have control over. You can have control over one or the other. And what we've done is taking control of the type. That is, we've said we'll just create a new type, and then we'll implement the foreign trait for our own type. It turns out that all we're doing is wrapping the new one. Oh, sorry, wrapping the old one, but that is fine. Okay, so test case list. Implementing the format display for a structure where the elements must each be handled sequentially is tricky. Problem with write generates a result. Proper handling requires us dealing with all the results. So this is going to actually talk about how to deal with the problem that I just dealt with. And with question mark available, implementing format display for a vec is straightforward. And this is a similar thing. We've got list. And our list is a wrapper around struct. Note that there's two forms of struct that we can provide. Essentially, they're more or less equivalent, except for the fact that this syntax with inside parentheses provides indexing by integer, whereas the other form provides named arguments. And now is a more extensive way to do it, so that one of the problems that I had was that the very last item had a comma, and that isn't quite grammatically correct. And a nicer way to do this is to call enumerate on the iterator returned by iter. This is complicated because if you are new to Rust, you don't know what an iterator is, or like what iter does, or what enumerate does. So this is going to be a hard thing for me to talk about in the 20 seconds or so. We've got a vector, which is the zeroth item of self. So self is a reference to a list, and the self.0 is a reference to this vector, and it has an iter method, which is another thing, a third type that knows how to iterate over the list into the vector. And so there was a really good question around whether or not a vector is mutable, whether or not versus an array. Mutability is slightly different if we say than what so a vector can grow and shrink. Arrays are also mutable, or at least you can opt into mutability and swap or adjust or alter the contents, but you can't actually shrink or expand the array. It has a fixed width in memory, whereas a vector is dynamically allocated and can adjust its size over time. However, both types are immutable by default. You need to have a special keyword mute or mut that will enable you to opt into mutability. I'm carrying on. So we've got a vector, which is the internal thing, and it has an iter method, which returns an iterator, which is something that can be used in a for loop. And iterators have their own methods. Iterators have an enumerate method, which will return yet another iterator, like another type as well, that provides the index or count of the number of times we have iterated, as well as the original iterator. And so you might be more familiar with using I as the index variable here. So and it's saying when it's zero, when it's not zero, then add a comma. Otherwise, essentially when it's and then but also print out the item in every case. There are other ways to do the control flow if you want, but this should print out 1, 2, 3 in a way. It should look like this. Actually, that's how. So let's look at what this prints out. We've got 1, 2, 3, and our activity is how do we print out something that looks a little bit more like this. So what we want is to print out that. And so we've got our I, which used to be called count. And there are multiple ways to do this, but I think this is probably the fastest. And most consistent, and now we have the output that we want. Okay, cool. As you make your own way through all of this code, do feel very comfortable with going into all of the other pieces of your of all the other references that are provided in the see also links, because they're really, really helpful at expanding your knowledge in a very specific way. We've talked, okay, let's talk about formatting. And we're spending a lot of time on printing things out and iterating across them. And that is primarily because the command line utilities is really, really important. We've seen that formatting is specified by a format string. I've got same variable foo can be formatted differently depending on which argument type is used. This formatting functionality is implemented via traits, and we've seen display a few times now. And here is a city, and it also has a reference to a string slice. Sorry, it also has a reference to string, but there is a special lifetime static, which means the entire lifetime of the program. So we didn't require specifying our own lifetime parameter, which is where we started with. However, I want to make this slightly more explicit. So what I'm saying is that my city cannot outlive the name of the city, or because because Rust will guarantee that the city, the reference to some data is always valid. It's impossible to have a null pointer in Rust, and this is the way that it enforces that. And now we've got another structure, a red, green, and blue channel RGB, and we need an implementation of the format display trait for the color struct so that the output displays as this. Here are some 2 hints if you need some tricks. Okay. Aha. So let's just check about what we print out right now. Oh, I wanted the city parameter. Now it turns out that because we are providing string slices, we are providing string literals. These last the entire length of the program. So I'm just going to go back and not confuse things even more by reintroducing static. Hopefully our program should compile. And now our job is to adjust this color output so that it can. So it's currently, we're relying on debug, but what we want to do is implement display ourselves. We can just copy this across. So this is the implementation for city. We've now got color, and the job here is to print out something that looks a little bit like this. Okay. What is an example issue that may arise if you hadn't used the lifetime trait for city name? So lifetimes are not traits, but so the lifetime syntax, what the error I received earlier was that the lifetime was specified in city, but this lifetime wasn't propagated, or the lifetime wasn't provided in any of the implementations. And it said that one of the options that you could have done was to provide the quote anonymous lifetime, but then I realized that this would actually just introduce more syntax, which is even more confusing for people that are just starting out. And so yeah. So I thought it would be better if I just stick to the job I've got. Okay. Which is to try and get this. What we're trying to produce is something that looks a little bit like RGB. Formatter comes first. RGB, question mark, and then there's something in here. Something in here. Oh. Yeah, question mark. And then another one. Okay, so I've got self has a red, green, and a blue channel. Now that is all fine, but we've got a problem over here, which is that we want a hex code. And this looks like one integer, but actually it's kind of not. Can anyone see what I've done, which is a problem? Like, it looks like we're creating one thing, but actually what we need to do is manually add 0 and x. And now I need the hex code for all three of these. And then ask, so that is with x. So now I have all three integers. And remember how we could use the integer version? We can do the same thing again. And so now we have red, green, and blue. But if we have zeros, I am pretty sure that it won't look right. They're not propositional. Oh, sorry, that's a mistake. 0, 2, and 3. What I want is 0, 1, and 2. I didn't actually invoke the wonderful implementation that I had. So let's do that. I should just delete all of city because it's hardly relevant. Expected. Wrong character deleted. So we're close, but we've got 0, 0, 0. What? What we want is 2 zeros. So to do that, we add 0, 2, which is just we say we want a pad with zeros and we want 2 of them. Yes, we have what we want. Not quite. We've got a slightly distinct. We want capital letters. Oh, so to capital letters, we use X, and X. Now, this is a bit of a trick because I'm meaning I could shift all of these. Do I do that? So this is a sort of a bit of a challenge, and the challenge that I've been given, I'm just going to move me up, is to push all of the data into one integer. Now, let mute. And it's a U32. And my self-read channel. So what I need to do is shift the bits from each of my channels into the right position in the binary. Actually, and so I've got all 0 bits to start with, and I could have started somewhere else. I could have just but let's go with what's intuitive. I want the green bits to be right on the right. So I can just say RGB plus equals plus and equals green. RGB. I'm probably going to get this wrong because I'm doing this off the top of my head. We want it and equals and we need to shift this how many bits to the left? 24, I think. And then this one is 16. If this makes no sense at all, please don't worry. But what we're doing is doing individual bit manipulation, and we are sending the red channel into a 32-bit or 4-byte integer and shoving them to the left, and then the blue channel fits in the middle somewhere, and green goes into. Now this is not right because but that's in principle what we do. This is syntax here, which is take the bits that you had and update it in place. Or do I actually want that? Oh, I will let someone else do the bit shifting. I'm sure that someone is going to come along and do it really well first go. But I need to carry on. We're actually, I just realized, like, there's no way we're doing this book in 4 hours. I've just spent an hour on the first chapter. Oh well. Okay, so that was definitely, of all the I'm prone to overestimating or underestimating, but that was one of the worst. And I'll hide my name as well. Okay, so let's carry on with primitives. So sorry about this. Hopefully it's been fun. I'm not going to be able to. I'm really upset because I was like, oh, I was doing so well with like 10 minutes per page. But actually it's 10 minutes per chapter, and each chapter has multiple pages. So I'm doing bad. Scalar types. Signed integers. Unsigned integers. Rust has a whole family of integer types, and this is extremely annoying for people who come from other languages, because Rust is extremely pedantic about how things are laid out in memory. There are these kind of slightly odd looking integer types, which are isize and usize. The size means the number of bits that is relevant for your CPU. In most computers in use today, most computers that you use as a human are 64 bits. Now, if you are thinking about all computers in the world, like the computer that's on my watch is probably not a 64-bit CPU, or the computer that's in my microwave. They might be microcontrollers and they'll have different bit widths, but let's ignore that for now. Floating point numbers are a smaller set. There are 4 bytes wide and 8 bytes wide. Characters are a single, is a single quote letter. If someone who is used to a script that has a single a single this form numeral represents the number 4 in with a single image glyph, and we've got A, alpha, infinity, and these are all considered single points. Now, some scripts that humans use are much more complicated than Latin-based text, and so it's very fuzzy as to what an individual letter actually means. And to deal with that, the character or char type is always 4 bytes wide. It's always 32 bits, which means that there are 4 billion different options available to your computer for deciding how to encode a specific letter. A Boolean type is either true or false. It's encoded as a single byte. The unit type is similar to a Boolean in the sense that Booleans have a very restricted range. A Boolean's range is 2. It has true or false, whereas characters can be one of 4 billion. The unit type can only represent unit. It is used for none or something like nothingness or emptiness in Rust. Despite the value of unit typing in tuple is not considered common type. Okay. Okay, compound types. Arrays, like 1, 2, and 3. And sorry, I'm slightly distracted because I'm reading some really nice comments. Please keep this video up after you're live, as you've done really well. Thank you very much. The recordings will be live. They will be available. I'm also happy, hopefully, to spend a little bit more time than I've allocated myself, 4 hours, but also there's a little bit of buffer time. If people are still with me, which I doubt, then that's available. I'm also somewhat tempted to do more of these at a very similar time, and so we can actually get through the whole book. If people are interested, please do subscribe, and we can carry on. Okay, compound types. There are arrays and tuples. Arrays have square brackets. Tuples have parentheses. Variables can always be type annotated. In fact, they always have a type. There are no dynamic types in Rust, really. Numbers may be additionally entered by a suffix or a default. Integers default to I32 and floats to F64. Rust can also infer types from its context. And so when talking a lot about primitives, pretty easy. There are no... let's just print this out and see what happens. Oh, in fact, there's no point. It doesn't have any output. So let's carry on. Oh, there was one point that wasn't made in the text, which I just want to re-emphasize, and that is mutability is denoted by this mute or mut keyword. Rust will always default to safety. That is, variables are immutable by default. That's one way I think to think about it. Type hints are provided with a colon syntax, and integer literals also have a separate syntax. I also want to introduce one other thing, which is underscores. So it's conventional in a lot of Western numeric handling of numbers. Indian, for example, is distinct. They've got their own ways of dealing with numerals, but the convention is to add some sort of delimiter, either a comma or a dot, depending on whether or not you're from Europe or not, and every third number. And you can do something similar with the underscore in Rust. Okay, we now have, let's talk a little bit more about Rust. We've got literals and operators. Integers such as 1, decimal numbers or floating point characters, booleans, and the unit type have a literal form. Integers actually have multiple forms. They could be expressed using hexadecimal, octal, or binary notation as a prefix on the left-hand side. And if you want to include provability, you can actually include number underscores and scientific notation with which expresses the number as some power to the 10, I believe. So this is 1 power to 6, which is 10,000, a million, and becomes an F64. We also need to tell the compiler the type of literals that we use. Not every time. Remember that we just had the default of I32 and F64. There are also several operators available that we've seen, such as addition, subtraction. We've got the unitary minus, so we can support negative numbers. That's useful. You do have Boolean operators, so true and false evaluates to false, whereas true or false evaluates to true. Not true is false. Bitwise operations apply essentially. Well, I actually shouldn't. I don't want to discuss bitwise operators in too much detail because if you know them, you already know them. And here are the shifts that we touched on before. Tuples is tuples are collections of values of different types. That may be different types. There's no requirement. Tuples are constructed using parentheses, and each tuple is itself a value with a type signature, where T1 through to Tn, where T1 to etc. are the types of its members. Functions can use tuples to return multiple values, as tuples can hold any number of values. Essentially, they can grow as required. So we've got a pair here of some I and some Boolean, and we would kind of invert them back. Interestingly, it looks like we're returning multiple values, but what's actually happening is Rust is creating like a little baby struct type in the background and returning a single argument back. If you care about the way that the assembly is looking, the way that the assembly looks under the hood, the following struct is for the activity. Matrix multiplication. Please implement. To do, uncomment the above 2 lines to see the compiler error. Activity. Add the display trait to the matrix struct. If so, switch from the printing to debug format and display format the following. I don't want to do this. Partially because I'm going to get my linear algebra incorrect. Partially because it's yeah, I'm gonna get the linear algebra incorrect off the top on the fly, and it's a fun thing to work on yourself, and I don't know if it is going to matter too much. An array is a collection of objects and slices. So arrays and slices, array is a collection of objects of the same type T, so they must be the same type, stored in contiguous memory. That is, inside the memory address space, they are right next to each other. Arrays are created using brackets and their length, which is known at compile time. That is, arrays must be of fixed width. They must be of fixed size. That's how they work. And it's part of their type signature is T length. That is, the length is actually encoded in the type. It actually disappears in the final binary because it's used by the compiler, but it isn't required actually in the binary itself. Slices are similar to arrays, but their length is not known at compile time. Instead, a slice is two-word object. So we're using some jargon in a very particular way. First, a word. What is a word? Well, a word for a computer scientist is the width of a pointer. And therefore, so slices are two words or two pointers wide, otherwise known as like two. Let me. You can think of a slice as u size. That's what I mean. It turns out that things are, let's just say, kind of like that. Similar to arrays, but the length is not known at computer. Now the word size is the same as u size, determined by the and the other jargon is object. Now object just means some value in RAM. It doesn't mean object in the sense of object oriented programming. It just means some value that exists in memory. Slices can be used to borrow a section of an array and have the type signature of an ampersand into a array of type T. Can you make your inline video smaller? I can. I was tempted to actually, but I thought that while I started, I should keep it big. How's that? Then fixed size type signature is superfluous. We don't need it because integers defaults to i32, and elements initialize the same value of 5. We've got 500 zeros in here, and I could change this to say 500 tens. Indexing starts at 0. The length method is the number of the length method is the number of elements. Arrays are stack allocated. So this means something interesting if you are working with RAM. Or sorry, if you are interested in systems programming and you care about where your data lives. It turns out that Rust is very stack heavy. It's almost the opposite of Java in this regard, that Rust will always prefer to use the stack unless it really needs to allocate on the heap. This is one of the ways in which Rust is very, very fast. Arrays can be borrowed automatically as slices, which is where we take a reference to an array and it comes back as a slice in local scope. And so slices can point to a section of an array internally with a range, and there's no need for a space in here. So it's just in the middle. Some bit in the middle of our backing array. So we've got Y's. Where's our Y's? There are our Y's. So we've got our 500 zeros or 500 tens. And there is also an example. We can actually refer to an empty array with a slice. And there's no distinction really between a slice of an empty array and a slice of an empty array with a range to all of the elements. So if I omit the start and the end, I get a range of the entire span, where I could start get 100. And I just point back into whether or not the stack and the heap. So I mentioned that Rust is very stack heavy. Do I personally spend a lot of time thinking about the stack or the heap? Well, kind of, not really. But that is because I've spent a lot of time working in Rust, and I sort of almost always prefer the stack. But if I know that I need to dynamically allocate RAM, then I will know that using a vector, for example, the vect type that we played with earlier, is actually a very useful. We know that we're going to opt into the heap and that it's available if we require it. Using the stack tends to create a significantly more deterministic use of memory than using dynamic memory allocation. It's also it means that you have fewer shortly lived objects, and you avoid memory fragmentations, a whole bunch of other stuff that means that your program just runs a little bit faster. Arrays can be accessed using get. Get will return something that is an enum, has some and a none. So if there's nothing available, that means that you haven't got, if there's nothing available, then you get this none out, which is distinct from unit, which does actually represent nothingness or emptiness in some cases. So a function will return the unit type. It doesn't return none. None and some sort of live together, and they're actually defined within a single enum, and we'll get to the single enum called option that we'll get to later. But I sort of can't help actually no, we'll get to it later. There is a nicer syntax rather than using this very, very verbose match, and we like pattern match on exactly what we want. But we so we'll carry on talking about integers and indexing and arrays and slices. If you take a slice of an array and you ask for something that's outside of its bounds, you'll receive a runtime error. And therefore, with slices, it's more typical to see the use of get, whereas arrays, Rust knows how wide things are at compile time, so it can actually cause a compile time error. However, arrays typically are less frequently accessed directly than other types. Oh, so there was a question, what is sum? Like, sum is returned from get. So I could think of this is maybe a val, maybe an x. So I've got x's, lots of typos, get I. And then and this actually is an option of two things. Actually of one thing. And it's an option of some type t, whereas t is the internal type of the array. So it's option of I32, and then I need to sort of go in and check. And an option has two variants. It is an enum, but unlike enums from other languages, the enums in Rust can contain data. And so I need to kind of go in and like inspect the internals and like pull the internals out. And so when I've got some value, I can use sum. I can match on sum. And when there's nothing available, so let's say I ask for I is actually well outside the bounds of the slice. Well, now there's nothing to return, and so I get this error message out, slow down. And this is a type which is relatively ubiquitous through the entire program. And then there's a question of like, hello, isn't it a reference to I32? And you know what? I bet it is. And so get doesn't provide you with the actual object inside of the array that it's getting. That is, it's not going to pass ownership to or the value never gets extracted from the array. Instead, what you get back is a reference into the array, which contains an integer. Thank you very much for the call out, by the way. They're extremely useful. Now, we've actually already talked about struct and enum in relatively large amount of depth, so hopefully we can rush through this one. We're about halfway through time, and I've done less than a quarter of the actual book. So, but I have spent more time in some areas. We talked about structs, units, what we know as zero size structs or zero size types, and otherwise known as markers. And so this could be, I don't know, anything. We'll just use the struct danger to, so a zero size struct might be useful when some function takes a type parameter, and you'll find advanced use cases for parameterizing functions with zero size types that mean that this type of pattern is useful, even though it seems very, very odd to define a type that has no contents. So every struct has a literal form. So there are no constructors in Rust. Instead, what we have available to us is the struct name, a curly brace, the fields, and then a close curly brace. And this is very rarely exposed to users. So in the typical case, library authors will define a new method that takes the parameters and return some value of the type, and that method, which is more formally known as a static method, is just invoking the literal form. The use of a static method improves the maintainability of the dependent code because it means that you are not required to make a breaking change if you update the actual items of your struct. So we can debug printing, we've seen a lot. Instantiating a point with name parameters looks a little bit like this. We can pull out individual fields with the dot operator, and this dot syntax means that you can update. It can actually Rust will be able to like inspect point, which is has a y value of 0.4, and create a new value with all of the parts that have been omitted from our new definition. There is the ability to assign new variables into so left edge, for example, and top edge are new variables that are being created from point. Now, so this is actually the use of pattern matching again, and it's one of the reasons why let is more general purpose than just assignment, because it's sort of fully it's more fully featured. To create a unit struct, which is this thing with no items, we just use the literal form as well. And activity, add a function rect area which calculates the area of the rectangle. Try to use a nested destructuring. Okay. I don't want to do this either. So, but I do want to show you how to implement a method. So we've been asked to implement a rectangle area that takes a reference to self and returns some F32. And the area of a rectangle, I actually just want to call this area because I've already got rectangle in the type. So there's a couple of things that we could do. We could say self dot top left. Oh, wait, whoa. We need the length of all. We need a height. So area is length times height. But all we have available is two points. And so we actually need to, so we've got top left and bottom right, and we need to create a third point so that we can actually calculate the length and the height, and we multiply those together to become the area. Now, we could do that, but I'm going to just allow the exercise to the reader there to be an exercise to the reader because it's not super useful, but essentially it would look a little bit like this. Oh, there we go. And well, so there's the actual code that we want. And all right, yeah. So what we do is we can actually be a bit smarter than calculating length times height. What we can do is, well, we've got two. We can take the difference, and which is essentially minusing the largest from the shortest or the smallest. But so the absolute difference will get some magnitude. And so we have the height there, and then the length we can pull out, multiply those together, and then we get the area. But how about I pass? Because I do want to skip a little bit further ahead. Enums allow the creation of a type which will be one or few variants. Any variant which is valid as a struct may also be valid in the position of an enum. Just to double down on that, you can sort of embed data inside enums. They are more like they are closer to structs that closer to objects actually in object-oriented programming, where you might have, for example, an event type or web event, and there might be like a type encoded in there, and it's often a string, which is sort of like a tag, and you check your behavior depending on what the tag value is. Well, an enum is similar but different, and that the tag is provided by the compiler. And they are inspected, or sorry, you can, they work very tightly together with a match keyword. The match takes an event and will require that you deal with every possible variant. So I'm just going to comment out click. So we'll just say we know that our program will never have a click. And let's find out what the compiler does. The compiler executes this code and says, hey, whoa. Pattern web event click is not covered. This is one of the most important things about Rust, that you will always be required to deal with every single variant, which provides significant safety because you will never have the problem where you accidentally forgot to deal with some case. Oh, I actually uncommented the wrong line. So I wanted to keep the click there are no clicks in our program. That click never appears at runtime. We'll now get a different warning, which is that, whoa, will we? Why is that happening? Did I reload? Let's try and recompile. Aha, the compiler was happy. You will sometimes get warnings which may have been silenced by the output. The warnings don't propagate all the way through to this interface. That your variant is never constructed. But that isn't a fundamental error in the same way that not handling it would be. It's possible to create a type alias whereby we have some short name or a more simple name than what is provided. This is often used when you have nested types or type when you have lifetime parameters. It's less. I've actually never seen people shrink the name of some variable down into something that they prefer, because they don't like very verbose enum of things to do with numbers. To provide more functionality to your local scope, you use the use keyword. Use will go and find some reference. In our case, we ask for the status. So status apparently can only be ritual poor, and you could be a civilian or you could be a soldier. It's a bit rude. Okay, so you can only be ritual poor in this little world, and the local scope main and can access poor directly, whereas if I avoid if I avoid the use statement, I would need to come and expand the type in full. You may have wondered, just by the way, where none and some come from. So we just saw those being used directly from a match after get, and it turns out that there is some hidden code. So Rust will implicitly, or the Rust compiler will inject a line of code, which is, I think, called use standard preload. And then there's a couple of different versions. So I think it's Rust 20 and 2015 or 2018. In fact, I don't think that 2015 is but each edition updates its own prelude, and the original prelude before editions were actually introduced into the language is probably called something like V1, and that does the same thing as what we are doing here for option. Now, there is a good point from Andre here, which is that we should not use the star syntax, which brings in everything from some other place into our local scope. Because, for example, we could go and create some other job title. So we might be farmer, but there might be some other use of, like, we might have said that type farmer is rich. In our world, farmers are wealthy. And now we've automatically created confusion between what the name farmer actually means. Okay, so let's pull that. And civilian. Okay, good. Enums can all be used as seed-like enums. That is, you can provide a default value. In this case, we've got fully saturated reds, greens, and blues in the enum value, and you will, whereas you could define the, so this is implicit. So enums will automatically use integers. Oh, sorry, they do use integers under the hood, and they are, so they are actually the same as tagged unions if you have ever used C. But you could actually go and change this to whatever you want. There are some further rules that relate to how enums are actually represented in memory. So it's possible that you can force the representation to be a single unsigned byte. Or you could say, I really need number to be a 32-bit integer. And Rust will do its, will follow what you ask. There is another, there's another part of this whereby number will require that you, sorry, I wanted to also introduce the fact that where there is space in structs, Rust will also implement, provide padding bits, but that isn't as relevant for enums. Whereas structs, there are some ways to force lists, force structs to behave like C, whereas Rust will optimize the layout to align with bytes and so forth in a way that the C language does not have available. And but let's talk a little bit more about enums. We can use we can create a linked list type using a cons and a box. So a box is some item on the heap. We've got a new one, and remember the static method new is conventionally used to denote a new item. And so we default to the empty list. Consumer list, return a list of the length. So we need to go through all of the length and can all of the items, and for every cons item, so this terminology comes from Lisp, then add a 1. And so this will be a so we get all the way through until we hit a null, and when we hit nil, the recursion stops. Notice that the recursion here length is this call. Oh gosh. Now there's a bunch of comments around how in Rust 2018 this changed slightly, but I'll just skip that for now so that you can read it later. The Rust language has improved over time and may become more simple so that it's easier to deal with for things like borrowing and so forth, and also lifetimes. The big point to make is that you sometimes take a reference when you might have otherwise defaulted to borrowing. And got prepend. I wonder if we have an activity. Communication timeout. So what might have happened is the Rust playground has gone and rate limited me. I was worried about this. So I'll just keep going for a little bit longer. And if it has said, no, my IP address has had too many, we won't run compiles. And then if we get into a problem where things become really difficult, I might have to hang up early. I was considering running the playground locally, but they couldn't figure out how to tell Rust by example to go to my own my own version of the playground. Anyway, constants. It's possible to define constants in Rust, and to make things more confusing, there are two forms. There are statics and constants. A static variable is one which is fixed in place. It exists in the a static variable will only exist once in memory, and then whereas constant will be copied into every location that it's needed, which sounds like a strange thing to do until you think about the different ways that these types are used, and or these keywords are used, because they facilitate different use cases. A static is typically used for global variables, whereas constants are often defined in global scope, but they are used in smaller places. And the compiler will potentially, in this case, we've got is big. So is an integer larger than 10? It might have some specialized form, which would mean that it makes sense to be able to it might make sense to have multiple copies. And I just realized now that I could teach you something else. So I've got a method here is big in. But one of the things that's quite let's just define so if it's big, then it's definitely not small. And in this case, it seems kind of redundant that we have defined threshold. Actually, the other way. Let's now make two copies. So we've duplicated threshold. If n is 10 equals threshold, then it's neither big nor small. But yeah, we can't modify the use cases that are enabled with statics is that because there is a fixed place in RAM, you can actually go and mutate a static. Yeah, using a interesting keyword. I'm going to do a different activity, which is I'm going to just introduce unsafe. And unsafe will enable me to update language. And let's say that we wanted to say that it's Haskell, let's say. Right, is Rust Haskell? Well, maybe. And the unsafe keyword will enable you to tell the compiler, I promise to uphold what you would do. In terms of the unsafe keyword is available when you can verify yourself that you maintain the guarantees that the Rust compiler itself guarantees. And in particular, there is only allowed to be one mutable, one place in RAM that has write access to any given value. And being able to update a static is something that requires unsafety. So there's a really good comment here around unsafety and how that is actually one of the things that is really important to understand. I'm just going to note that down as something that I want to flesh out in a future video, because I don't think that I'm going to be able to give that sufficient depth right now. But I really do encourage you to kind of monitor me via, like in this case, LinkedIn or YouTube, and I'm going to try and provide a really thorough explanation of the semantics that are enabled by unsafe and what it means and what it doesn't mean. Just very quickly, it doesn't mean that your program is unsafe by it doesn't. What it means is that the Rust compiler can't verify that the operation is safe. The onus shifts from the compiler to you. And that's essentially what unsafe is doing. Okay, let's talk about variables. I've talked about them a lot, that they use let. And the one thing that's new here is that there is an underscore. I can use the underscore in two forms. I can give it a name. I can give some variable a name, which is kind of self-documenting code, and this will silence any compiler warnings about unused variables. Otherwise, I can just use an underscore to essentially erase a value, which is surprisingly handy when you have some things that are annotated with, quote, must use, in particular a result, and you don't mind if you and you want to explicitly say that I don't care whether or not the result succeeded or failed. All I want is that the action was attempted, and the underscore will enable you to do that. Just a very quick follow-up on, is unsafe a vector of an attack? Yes, vector unsafe is a very significant vector of attack. So what this means is this is in a security context. The Rust compiler no longer is able to verify some of this. So it's still Rust language. So things like you can't go and create, you can't refer to memory that's invalid. Rust, but if you want to pass, if you want to get a pointer from some foreign function, so let's say that you've pulled in zlib or you've pulled in libjpeg into, so this is a C library and you want to invoke it from your Rust code, and C libraries typically provide you a void pointer. That void, the Rust compiler has no ability to go and introspect what is going on in the third-party library, and so your Rust code is still vulnerable to any security vulnerabilities that are that are in that foreign function. There are other things that Rust will require unsafe for, such as interacting with the operating system or with hardware devices. By definition, the Rust compiler doesn't have access to what the operating system does, and therefore, if you invoke a syscall, you are giving the kernel access, like sort of privileged access to you as a program. Like, well, essentially that has to happen, but the Rust compiler can't verify it itself. Okay, let's carry on. By the way, I'm more than happy to kind of go into these tangents, because that's actually the advantage of watching live. And I really want to say to people that that do ask questions and do really want to learn more, that this is your time. This is getting through all of as much as Rust as possible is useful and interesting, but the real advantage comes in participating live. I'll just do a very, very small plug, and that is I am going to try to run live courses more frequently, probably for a relatively, so in two forms. One will be actually three forms. One will, the cheapest will be things like this, where I go live on public live streams. There will be a closed version, which essentially is a low fee option whereby you can ask questions in the comments, such as you're going through now, but the audience will be much more restricted to people that have paid. And then there will be a higher priced option, which will be restricted even further in terms of like have max capacity of say 6 people. And I will just stop talking. I know we'll just work through things in complete detail, and we'll all chat to each other directly in through Zoom, for example, and that will be much more of like an online course. If any of those sound interesting, please do send me a note, because I'm trying to use this as a trial run of each of those formats. So I'm really delighted that people are enjoying the content. Please do subscribe and follow and like and all the rest of it if you would like. Okay, cheers. Let's carry on with mutability. Everything in Rust is immutable by default. For people that care about the way that programming languages are implemented, though, the mute keyword is very slightly deceptive. The Rust compiler doesn't actually care about mutability. What it cares about is aliasing. If you don't know what aliasing is, please just close your ears for a few seconds. Rust will prohibit the ability for multiple references with write access to any given value in memory. It will prevent multiple aliases of the same data. That is what is provided by mute. That is, mute will enable what is in C++ a unique pointer, or is called a unique pointer in C++, and the Rust compiler will kind of enable one of those to be given out. The downside of calling it mutability is that there is a feature of Rust called interior mutability, which is where we have a read-only or an immutable binding to some name, but you're still able to update the value. And this seems like a completely mind-bending trick, but it turns out there's no magic, but for the fact that you are working through an intermediate type called a cell, which has full access to the data, and the Rust compiler is guaranteeing that the memory layout and so forth is correct. However, and you are still able to update the actual value without getting into trouble with with ownership semantics and so forth. And it's extremely confusing if you think of immutable and immutability and immutability as complete complements, because Rust provides this kind of awkward middle ground called interior immutability, which enables you to change the value of immutable objects. Now, this paradox is broken somewhat when you realize that the Rust compiler cares more about aliasing than actual mutability itself. It's a really, really good point that the box type in Rust is essentially the unique pointer in C++. Is that accurate? I didn't realize that that in C++, unique pointer also allocates things on the heap. I know that it takes ownership, but I didn't realize that it will also implicitly allocate memory. That's an interesting point. Sorry if I'm getting really stuck in the weeds. It's just really fun. Okay, scope and shadowing. Variable bindings have scope, that is, they are not able to be accessed outside of where they are defined, and they are constrained to live in a block. A block is some collection of Rust code that is inside braces. And these curly braces here enable, we've got this shortly lived binding of a new variable that is assigned to 2, but we couldn't access the name shortly lived binding outside of the scope. This is, you could think of as spatial binding. A similar way of thinking about this is that you couldn't reference a variable that is before it is defined, that you might think of as like as a temporal constraint, and you could think of the scope as a spatial constraint. So this is going to be a command, a compiler error. Let's fix that. Just a second, I'm going to cough. I'm just recovering from a cold, so let's fix this. So the only way around this would either be to create a another variable over here, and then update it, or essentially move the print statement into the inner block. You need to update either the control flow or where the variables are assigned. You are Rust will allow you to rebind to the same name in a child scope or in an inner scope. And so we have 2 instances of the same variable shadowed binding that refer to exactly the same, to different data points. And Rust there won't be any confusion about which variable means, because of Rust's very, very strict requirements around references and all of the invariants that it supports. So just to kind of move through, we've got before we shadow, we are on line 5, and we have the variable assigned to 1. Inside the inner block, we then reassign or to create a new binding to ABC. Once we finish that inner scope, the variable name sort of reverts, or at least it's the same as what it always was, which is 1. And now we actually overwrite or shadows the previous binding. One thing that might be obvious, it might not. I just use the word overwrite, but this isn't overwriting in place or in memory. This is creating a new value which has the same name. The deletion and the deletion is at 17 at the end of the scope for both of them. That is when the data will be deleted in RAM. And this, and more formally in the Rust terminology, would be saying that the drop implementation is invoked. A drop is a trait that almost all types implement, which mean, in fact, I think every type implements. It would be weird to have a type that doesn't implement drop, which would mean that it would be impossible to ever free. It's sort of hidden control flow. There is like a call to, right at the end of the function, there is a sort of almost a hidden subroutine where we go through and we delete all of the variables that we've already allocated. So we could say shadow binding.drop, and implicitly, or the compiler actually knows all of the data, so it's actually able to drop everything. Even though it would be impossible in source code to access the shadowed variable. Okay, we need to declare bindings first and then initialize them later. It's highly irregular, but it's available to you. So we have some variable that is enabled to be initialized and we initialize the variable that we defined in line 3 on line 9. And the problem with this is you have issues relating to uninitialized values, and therefore you get irritating compiler bugs, which are actually very useful compiler bugs because they convent. It's much better to get a compiler error than a runtime error. And we'll just kind of move forward. Oh, now we're talking about data can freeze. And when data is bound by the same name immutably, so that is, I create a shadow of the original. I don't understand why there is an underscore here, but let's say that there is. And I mean, fine. Then we can actually, we encounter a problem, and that is, even though we've got a mutable variable up the top, it becomes fixed in place or frozen in place inside the local scope after the new binding. Wow. Okay, let's talk about types and type conversions. Actually, I'll just pause there very, very quickly. So we are at chapter 5. So roughly a quarter of the way through the book. And so far I've got halfway through my my time allocation. So I'm just going to pause very, very briefly and let people ask any questions that they might like to. And just remind everyone that you are very, very welcome to participate however you would prefer. I'm just also going to take a very, very quick break. And I'll be with you in just a second. uh, yeah, so apologies. let's carry on. uh, it's very interesting when you stop speaking that suddenly the comments go crazy. Okay, let's start that again. There are multiple ways to cast between types, and the fastest way is with the as keyword. The problem that we've got is this looks like we are converting between an integer and decimal, but it turns out that decimal is a floating point number, F32, and Rust needs to be given more information about how to apply the conversion because it's got enough space for a new integer, but this is of type, it's only 1 byte wide, but we're giving it a type that is 4 bytes wide. And because there are multiple options available to convert between one and the other, it's requiring you to tell Rust. And it turns out that the simplest way to do it was with as. There are others. So, but let's see what we get to. We can cast the decimal version, so 65.43 as an integer with U8. And now we are at 65, and then character is some integer, and then we convert that to a char. And I believe that would actually be the ASCII version 65, which I think is A. Error, there are limitations in conversion rules. A float cannot be directly converted to a char. So this character here can't go directly from floating point, which is the original 65, to a character. You could sneakily do it this way. But that's slightly ugly. And when casting fits into a value of an unsigned type t, tmax plus 1 is added or subtracted until the new variable sits into the new type. 1,000 fits into, so 1,000 defaults to I32 because it's just an integer literal, and it will automatically fit into a 16-bit or 16-bit or 2-byte integer itself. You can stick 16,000 in there, and but 256 doesn't fit. Sorry, 1000 doesn't fit into a single byte. There are only 256 values, and so it keeps shrinking them down until it fits, and everything else gets truncated. Now we've got a problem though, and whether or not this is intended behavior or not, and is up to you. And you won't receive much runtime information about what you're actually doing. And so it's, in my opinion, not very sound form to use as conversions because you can run into subtle bugs because you might not have intended to create the value 232. Instead, you might like to report to the user, oh, somehow we have a type that doesn't fit, or we could add an assert. We could even crash the program. If our variable was larger than, say, 256. Now, or if you wanted to do this at debug time, we can add debug assert, which will be erased for our production builds, but during testing for our debug builds, we have the ability to crash the program if some parameter is out of bounds. Talking about how to all of these different types of conversions, and then there are unsafe methods which will provide the conversions, and then there'll be no no help provided if you try to convert not a number type to an integer. It will just work, but that might not actually have any meaning at all in the type that you are converting to. And so this will depend on numeric literals can be annotated with a type. We've done this a lot already, so that's good. That is, you can provide this, you can provide a literal with a type. Now this is useful if you start to have different syntaxes. So for example, I might say sum of 100 unwrap, or you will get into parts of Rust where the functional style will ask for values to be provided in line, and in those cases there will be fewer opportunities to provide type hints, and the this suffix literal syntax is handy in that instance. It can be slightly awkward to read, and so I often put the underscore in there as well. Type inference is quite common in Rust, particularly with containers. And even though we have a new vector here, and we could say we can initialize a vector in multiple different ways. We can add new elements to it, and Rust will be able to infer the type of the vector, which is, it turns out, this type here. It's a vector of bytes because it's the same type of the elements. It doesn't need any of this information because it can infer it from context. We've got a square brace and then a 5, which is helpful. This sort of halfway, this sort of half definition of a type is relatively common because sometimes we only want to tell Rust what the type of the container that we want, but Rust has enough information to understand like what the contents will be. And so another option is, actually, let's not go into further Rust, but I just want to point out that you can actually provide an underscore as a valid value. Hello from New Zealand. It's really nice to see my friends and colleagues from other parts of the world. And it's just a real delight to know that we are kind of all in this journey together. The type statement can be given a new type. We've seen type a little bit before, and one of the use cases for this is to provide some self-documenting code whereby we want to use an integer, but we want the source code to tell us what unit to actually be provided. In this case, we've got inches, and we definitely want centimeters. Let's see, we got inches. Even though the actual type will be an inside integer, and the and one of the things that you'll find in your expedition of Rust is that you will encounter multiple definitions of result. another thing that you'll find multiple definitions of is error. And it turns out that modules will alias or create their own alias of a result with their own specific error type. So they provide their own error type, in this case IO, and they shrink down the number of type parameters that result provides. So result has two. It has a type that you can provide when everything goes fine. You can think of a try catch statement in language with exceptions. A result will provide the true, the try side as well as the exception side. Result does the same thing, but it enforces at compile time that everything will be dealt with via the pattern matching that we've dealt with before. Okay, conversion. So we talked about casting, and now we want to actually convert between types, which is a more explicit way to, which is a safer alternative to just using the as keyword. And they rely on two complementary types, from and into. That is, we can convert from one type into another, and depending on which side we start with is which method we call. You could start with a what is known formally in the type system as a string slice. So a string literal is not a string. It's one of the most confusing things about becoming a beginner Rust programmer. A string literal is a reference to a span of bytes which are valid UTF-8. So in the local scope assigned to my stir is a reference to some other data. Now, a string with a capital S is slightly different, or it's not just, is different in its implementation and its semantics. Just want to say, like, a big thank you. It's a very, very nice thing to say, Elton. I'm going to treasure that comment. I just want to say, that's a very, very nice thing to say. So a string will take the data that it refers to. So in our case, we take a reference to some UTF-8 bytes, and it allocates its own space for those bytes, and then copies the data across, and then marks the original data as no longer valid to access. So string now has full control over all of the contents of my string has full control over all of the contents, whereas my stir has no ability to go and modify, expand, contract, shrink, or grow the thing that it's referring to. If you have a string slice, you have no ability to touch the memory. You can have a mutable slice, which is slightly complicated. You can change individual bytes inside it, but you can't grow or shrink it. There's no dynamic memory allocation. Ugh, I need to get onto conversions. Okay, use standard convert from. I've got a number here. It contains a value, which is an I32, and I want to be able to convert from the primitive type into the number, which is my specific number. And I might, to make this more useful, I might say this is a temperature, and these are degrees Celsius. Except I always, and it might actually make sense to say that this is Celsius, and the unit is encoded in the type system, but let's pass for now. And then By the way, fun fact, the 20 degrees Celsius is an integer in both Fahrenheit and Celsius. It's one of the reasons why 20 degrees Celsius is often required in the ambient temperature of many scientific experiments, because it is a comfortable temperature for humans to be at for physics experiments. That's just fun geek fact. But carrying on, so my number is temp, 20 degrees, and into is the kind of inverse, but instead we start with the we start with the integer, and then we give it a method. We kind of with into, and notice that it uses the dot operator. The dot operator, it takes a reference to, in fact, not a reference, it takes self by ownership, but it takes a self parameter, whereas from does not take a self parameter. It is a static method on the type. It only takes the thing that we are converting from. It takes a by value as well. So this integer is always taken by value in both instances, but it kind of depends on where we are coming from. Typically, you will find yourself going the route of implementing from, but calling into, which strikes me as is kind of odd, but necessary. These are complements, but there are some very, very subtle edge cases, which mean that these are two distinct types, and it provides Rust with more robustness overall. I'm glad that the next chapter is oh yeah, by the way, don't worry about the boilerplate of having to implement both traits. It turns out that if you implement from into, the other side is automatically implemented for you. For various reasons that relate to ownership, the into implementation is, I'm going to get this wrong, but I'm just going to say is easier. From is slightly more is slightly more complex, and so you only need to implement one. The other one, the compiler can deal with by itself. Once you've provided from, into is provided. Now, what I recommend is actually starting right here on try from and try into. So this was introduced in Rust 1.34, so it's relatively late. We're now in, it's now September 2023 as the recording is being made, and I'm at Rust 172. So try from and try into they've been around for a while, but they provide a result. The result type is an enum, which provides an okay side and an error side. It turns out that your result for so the try from, you'll note, try from provides the possibility that your conversion may fail, whereas previously the from and into types could never fail. And that means that there was always a kind of an element of risk. In this case, we know that if we have an I32, we start with a raw over here. So let's say we start with A. Now A is an integer, and it might be 7, and therefore if we are going to create our even number struct, we need to be able to provide the possibility of an error. In our case, we've got a unit, and I'm going to just not a very satisfying error because it doesn't actually provide much use, except for the fact that essentially it says that the conversion failed. And so we can't get it from, we can't create an even number from A or 5. But now you have opened up or unlocked a bunch of use cases which provide the ability to take some external type, convert it to your own type that you can control, and you've got an escape hatch if that conversion fails. You might need to, for example, truncate or round or do whatever you need to do, or maybe even crash because it's completely unacceptable to deal with. Anyway, let's carry on. To and from strings. Okay. This is one of another things that there is also, just by the way, this is a very, very good point, that there is another thing that you can do, which is your error type could be infallible. There is this infallible thing, which basically says that, yes, even though it's an error, the error will never occur. So instead of saying from I32 for even number, we would just say will only ever return, it will only ever succeed. And that can be used or useful if you have something whereby you want to be able to really demonstrate to the compiler that the result is essentially not needed. And you'll probably find that the optimizer inside the compiler will say, aha, this is an infallible conversion. I don't need to worry about creating an actual result object. I'll just erase that away and your code will suddenly go faster. Converting to and from strings is a bit confusing because there are multiple traits and multiple types involved. The trait that you implement is display, but it turns out that instead of implementing instead of actually relying on display, what Rust really cares about at the type system level is toString. And weirdly, toString is itself distinct from into string. So you could also think of, what am I talking about? So you could think of conceptually, there is a implement or circle. You could imagine that we could be consistent, or even try from, for example. Actually, so from or try from. Rust has some sort of special machinery for strings. Strings are so ubiquitous that and they require special handling around that they've created the special trait toString, which happens to dovetail really nicely with the format machinery. Because essentially, if you can be printed to the screen, like on the terminal, by definition, you can be converted to a string. And there is a really neat method which will involve a really, really neat method that is available to strings, which goes the other way, which is, again, it's sort of the inverse of toString. So here we said that we had from string for circle, and I actually want to essentially implement from string for I32. And we do that with this from stir trait, which again is a sort of specialized machinery for the job of parsing from raw text. Now, parse takes a type parameter as well as a value. So the value is the implicit argument self, which in the line 2 here is the numeral 5, and the type hint comes via the context of the type inference machinery. You can see with turbo parsed makes use of the so-called turbofish syntax, which is there's colon, colon, square brackets, and I'm just using the underscore here, but I could change this to whatever I wanted. So let's say that I wanted a floating point number, and I'll now get an error that we need to convert between, I'll just do that one, F32, between the two different types. And so I'll say that parsed actually needs to be as F64. And now I have an accurate sum. The parse method, I've got this unwrap thing. So do you remember, and we actually haven't dealt with result very much. So do you remember how result was an enum, and it has two type parameters, T and E. And one is okay, T, and the other is E. Oh, and for error, and it's the error type. It turns out, I say that a lot, don't I? Most of the time, we will encounter okay. So most of the time, we'll have text input that is actually a real floating point number. And in our case, it's using the scientific notation. And so it's 5 to the power of 12. No, 5 times 10 to the power of 12. And if I think of result as kind of some sort of container, or like a present, like under the Christmas tree for people that celebrate Christmas, or a birthday present or something, and then I unwrap it, I get out okay. And if okay isn't there, if it's actually an error, the program crashes. So, and there's another way around this where I can provide some default value. I could say if it is if this isn't a valid number, let's say I've just got E12, or I've just got some miscellaneous text, well, I default to 0. And that might be what my application demands, but it might also be, yeah. So the appropriate thing might be to crash or ask for extra information, but the choice is over to you as the programmer, but Rust will force you to make the choice. When you use unwrap, you are telling the compiler that the data will always be valid, and if it is invalid, to crash the program. So slightly helpful, or more helpful way to do this is to provide a error message, and we can offer one with expect, and we could say not a valid number. Now, if the program crashes because it encountered invalid input, you now have a specific error message that you've provided. Talk about expressions. Now, this is an interesting statement in natural language, saying that Rust is mostly made up of a series of statements. And you might think, well, what on earth is this? The reason why that's kind of an awkward thing to say is Rust is also known as an expression-based language. And so these things might be in tension. It turns out that, and I do say it turns out a lot, every semicolon is a statement, or at least, so that it expects an expression, and then the expression is terminated with a semicolon. But statements also have return values. They return the unit. So so main automatically, or returns unit implicitly, or any function that is defined without a return value automatically implements unit. It would be the equivalent of me just returning right this. And you might wonder why we've got a return keyword here. And I just want to point out one very, very silly thing, which is that the code generated actually in some sense has 2 units. So we're returning this unit here that I have in the source code, but the semicolon also has a return value itself, which is another unit. But the expression, the return expression, is returning its own one. There are a few kinds of statements in Rust. Most common is a declaring variable. Oh, let is a variable and expression. Variable bindings are expressions. Are statements, and so are expressions terminated with semicolons, and even blocks, as well as if statements, are expressions. So a block returns a value. An if statement, what is normally called an if statement is an if expression in Rust, and that returns a value. No, we're finally at control flow. It's only been 2.5 hours of my Rust journey so far. Here's if and else. So we create an integer, we assign a variable n, or bind the name n to the value 5, or an integer of i32. And now we can do some logic. So if it's less than 0, it's negative. Otherwise, if it's greater than 0, it's positive. Otherwise, it's 0. The if statement, this is a complicated expression. So it's on a separate line, which makes it more confusing to parse as a human. We have an if else block that returns a value as well as doing some other work. In our case, we multiply it by 10. So if it's less than 10 or greater than negative 10, and greater than negative 10. I see. Then we need to multiply it. Otherwise, we'll halve it. If you put a semicolon in at the end of the line 17, there is now a confusion at line 12 because the type inference doesn't know whether or not to put an integer there or to put the unit that is implicitly provided by the semicolon. This semicolon on line 19 is needed so that the let binding works, because let is a statement. We'll just skip that. We're now at the start of control flow and looping. I've actually touched on looping sort of by accident when we were looking at formatting. But let's carry on. That was a while ago, so probably we didn't have everyone with us. I've got a main function here, and I start with a count, and let's count to infinity. Let's go. I count to 1, infinity, and beyond. Once we get to 3, we jump ahead to the next iteration. And once we've hit 5, we say, okay, that's actually enough, so we can terminate it. And so we should print, well, it's pretty obvious what this prints out. 1, 2, 3 is a word, 4, 5, and then we we say we've done. I maybe should preempt a little bit of stuff that's coming up, but these loops actually can have, oh no, I won't preempt the rest of the book and just allow it to explain itself. Because I was going to say, these things take labels and you can actually break out of a loop right from the inner loop. And the reason why this is introduced is it provides something that is almost like a limited go-to statement. So the Go programming language, and in fact many others from its era, provide the ability to go to arbitrary parts of the program. And the reason why they enable this is to, well, one of the reasons is to sort of go to an error handling routine if some error condition is met. And Rust provides something similar but different in the sense of, if you are doing some processing in a nested loop and you encounter an error condition, one of the things that you can do is break all the way out of all of the nests in one go. Loops themselves are also able to return values. Now, this is one of the strangest things to think about, that your control flow, like that loop is just another expression. The reason, to me, this seems super odd because I think of loop as an infinite loop, but loop also returns a value. In our case, we are counting, and once we hit 10, we then use break and we return a duplicate, we return 20. The one thing just to note that essentially everything in Rust, except for let and the semicolon, returns a value. While can be used as a loop, and we have a test, and this is a very easy way to implement FizzBuzz. I am going to actually cheat. Well, not cheat. I'm going to show you a way that I prefer to implement FizzBuzz in Rust, which is with a match. maybe I shouldn't bother. Match in, and then I can say, actually, I'll just do match in modulo 15, modulo 3, and then 0. In cases where we hit 0 here, then I can print out FizzBuzz. The underscore will match anything. If I get 3 is 0. Oh, that's right. Thank you. This one is 0. Then we are fizzing. We're buzzing. Oh, that's wrong. Otherwise, we print out in. We can actually simplify this even further by returning a value from match, which is our the thing that we want to print out, and then having a single thing print line at the bottom, and that will work fine. There is another alternative to which we'll probably be able to see in just a second. Instead of manually incrementing a counter, we can iterate over a range. So we simplify our code quite a lot. For loops, we just saw those. Yeah, and there's our fizzbuzz again. Okay, so this is a complicating, we now hit a point of Rust, which is again a little bit confusing, especially for beginners. We need to talk a little bit about the fact that there are multiple methods which return iterators. They look very similar, but they're slightly distinct. Well, no, they are distinct in terms of their semantics. The iter method is let me start that again. The iter method will provide a borrowed form of the thing that is being iterated over into iterator. So this is each of these, each time we encounter name, we get a reference. So you can see here that the match is trying to match on a reference to a string slice, and it won't allow, quote, the owned form. Ugh. Whoa, that's not what I expected to happen. Where did that go? I think I clicked on the GitHub page. And hello, Bob. Hello, Frank. There is a Rustacean among us. Names Bob, Frank, and Ferris. And if we take away the ampersand reference, it won't work anymore. The awkward thing about this as an example, or using string literals, is that string literals are themselves references. And so we are matching a reference to a reference of data. Inside names, there are actually references to things. So another way around this is to dereference name and match on that. That way your match statements don't seem as ugly, as long as you're not intimidated by stars and ampersands, essentially. But that's sort of over to you. If you have so another complication is when you're iterating over strings. Suddenly you can't match as easily on string literals. And I'll call myself a frustration here. So say if we get Ferris or Tim, then there's a Rustacean here. Now we've got Bob, Frank, and Ferris, and let's say that they're strings. But they start as string literals, and then we need to convert them into strings. The problem that we face is that the thing that we're matching against are not strings. So one way around this is to say we take name and then we call as stir, which is as a slice of string. Now, Rust has an automatic dereferencing policy. So if you call a method on an object, it will automatically dereference, in our case, name, and do the same thing as though we are dereferencing name, which is a reference to a reference itself. so that you don't need a whole bunch of parentheses and stars everywhere to do the automatic dereferencing. And an alternative, which Andre points out, is that if you iterate over a reference to, if you iterate over a reference to a collection, or in fact, to a vector, you will get the same behavior. That is, each name will itself be a reference. Excuse me. The one of the other things that's kind of complicated is that there is another method into iter, which takes your object and converts it into an iterator over the object. And it does this by taking ownership of the thing that you are iterating across or iterating over. So once you hit line 9, Rust's view of the world is that names is no longer valid to access. The reason why this becomes particularly complicated, because if you just use iteration over the variable, the compiler will actually insert into iterator into iter itself, and we get this horrible error message, borrow of moved value, which feels very annoying because you're used to thinking about variables as having local scope. There is no delete here. We never said to Rust, if this was Python, you'd be perfectly valid, or in any normal programming language, any reasonable programming language would have the ability to say, my variable is assigned in local scope. I accessed it and now I want to use it again. In our case, though, Rust has given ownership, in Rust's view, you have moved ownership into the child scope, and you have called into iterator. When the iterator is finished, so is the thing that it started with, because the conversion takes ownership of the ownership takes the into iter method takes ownership of the data. Sorry, my computer is getting quite jumpy, and it's actually highlighting different things that I'm not talking about, which is helpful. There you go. Good luck. It turns out my mouse is getting a bit jumpy. There's a third form which enables you to get mutable access to things. We won't bother with that. We've looked at match lots of times. You can match on different values as well as a range. And there was a really good question that's just popped up, which is that I spent a lot of time saying that would names be deleted here? The answer is probably not, but it's just marked by the compiler as being invalid to access.
My understanding is that the actual invocation to drop will happen later at the end of the function. But I am sorry, by the way, I'm losing my voice. Obviously, I've been talking for a couple of hours now. Uh, and apparently that's about as much as my voice can take. And also yeah. So this is all stuff that we've seen, except for the range syntax. We've seen range syntax with two dots. If you want to have an inclusive range, you add an equal sign to the right hand side of your dots. Oh, just to emphasize that there is a that Rust is more powerful than Switch. You will find that the Rust compiler will guarantee that every variable, everything that could happen is handled. So we're only dealing with a couple of prime numbers and some numbers in under 20, and that's not all integers. So Rust will complain. Match is one of the things that we're talking about now. We've got our match block, and the it can actually be used to access structured data. You saw this with when I implemented FizzBuzz. The most obvious way to do this is with tuples. So it's possible to create them anonymously. No, I start with a tuple, and which is triple, and then I can ask them, or I ask for them I've got a value 0, y, and z, or z. I actually didn't know until just now that I can use dot dot to access all of the other fields and assign them to variables. So I learned something as well on my way through my time here, which is kind of neat. Like tuples, arrays and slices can be destructured. So we can actually assign variables into individual items of the match, which is kind of fun. So I've got a variable here, second and third, that is available inside the scope of the match itself. And again, it can also we can also tell Rust to ignore anything else with dot dot. There is also this slightly awkward syntax called with the at symbol, where we assign a pattern to a variable, and it's a little bit more flexible than just assigning things directly. But I don't remember the details. I've seen this almost never used, but I know that it's around. And there are more details available if you really want to inspect like what's actually happening. Enums are also able to be used in a very similar way. You will find this in the Axum. In fact, multiple web frameworks will provide the arguments as if I can actually define a function that will destructure the arguments on each side, the variables RG and B are accessible only with inside the scope here on line 28. And it would be impossible for me to use elsewhere. It doesn't exist. Oh, the other thing that I've done is added these blocks, added braces, which means that I now need to put the comma in a different position. My voice is really starting to go. So I'm a little bit worried about my chances of getting all the way to 4 hours. Funnily enough, the different forms of color modeling, HSV, HSL, which is hue, saturation, value, CMY, RGB, and so forth. We link to the Wikipedia page in the documentation, in the book, which is fun. And now we're getting to some really, I want to say advanced stuff, but that's not quite accurate. It's very specific stuff for people that are using Rust for, quote, systems programming. Just a second, I'm just going to cough. Hopefully some of my voice will come back. Okay, so for pointers, a distinction needs to be made between destructuring and dereferencing, as they're actually different concepts, and they're used differently for languages like C or C++. Let's take a reference. So the variable name reference is a reference to an integer of I32. We can then match on it, and we need to match on a reference as well. Okay, right, I see. So the fact that we do have alternatives. Okay, good. Okay, we can match on a reference, and then we have destructured val into be to mean some integer value, and now we're able to use that val because it has gone into, you see that the matching is sorry, the distinction here is between a dereference whereby we go and ask for the value, and we see that if the matching parentheses are dropped, then the I32, why am I so confused? I don't understand. Are we comparing references against references? And I got confused by the phrase dropped. What if we don't start with a reference? The reference was so if we start with a value, we can provide, we've got a ref keyword, and it So underscore is a reference for a ugh, my brain's going. What if you don't start with a reference? Reference was not an ampersand because the right side was already a reference. This is not a reference, however, because the right side is not one. We uh, will usually see the ref keyword inside matches or instances in which you need a reference but you don't have one. I know that sounds very wishy-washy and hand wavy, like I'm kind of literally waving my hand, but we will find instances where you might have an option of something and you need to pattern match, and ref is a way to kind of circuit break, or kind of circuit break is the wrong word, is a way to get through. Accordingly, by defining two values without references, references can be retrieved via the ref and ref mute. But to actually use a reference of M for a mutable reference, we need to dereference the object. Now, I wonder if I can. So sorry, I did a pretty bad job at explaining that. I am actually somewhat unfamiliar with seeing ref used right on the outer scope, but maybe that's just me. I like this point that ref is kind of just pattern matching using the dereference operator. Because I think of ref as being handy with pattern matching, but not as something that I can just create with a variable for no other reason. Anyway, sorry. So let's move on to the next chapter, struct and destructuring. You can destructure all the way into the inside of a struct. So for example, I've got some struct foo, which has fields, which and x here itself is a compound type with two parts. And I can assign b to the variable b to the field inside a field if I want to. There is the possibility that not all values that you're matching against are what you want to match against. So we can provide an if guard, which will test whether or not the value we've just destructured some type, and I can go and apply essentially a closure or some function, and it's actually an expression that uses the variables that I've just defined that returns a Boolean. And if the return's true, then I can go all the way through. Otherwise, I'll match. Rust will continue to find somewhere else to match. The compiler won't take guarded conditions into account when choosing all patterns that are covered by the match expression. And you are, so what you're seeing here is that I've got an unsigned integer 8. Sorry, an unsigned integer of 8 bits, so a single byte that's assigned to 4. And if it's 0, it's it's 0. Otherwise, it's greater than 0. So we know as programmers that this is the entire range of the type. It's impossible to have a negative number. In this case, though, it might actually be more sensible to do something like that, whereby we just delete the last guard. The alternative is to have a wildcard pattern whereby you specify unreachable. The difficulty that this approach has is, what if you're wrong? Then we generate some sort of instability in our code. Oh, there is a question here about what happens if match cases have an overlap. And that is, what if you have multiple things that could match? The answer is that Rust will evaluate each option from top to bottom as they're laid out in source code, which has another side effect, which is that you should always have your most specific matches at the top. In our case, we are putting I, let's say greater than or equal to 0. Well, actually, let's just assign I. And we'll say it's greater than 0. And we have a specific thing 0 here. Let's see if this will compile. It does compile. But our little test here for 0 is never invoked. The interface that is provided by Rust by example silences a lot of warnings. And so if we were to run this in the playground, it would, or just in the Rust compiler, you'll find that it'll be much louder and will give you a little bit of a hint that you've done something that isn't really valid. Binding. Indirectly accessing a variable makes it impossible to branch and use a variable without rebinding. So now we are talking about this @ symbol and why it's used. We could, so in our case, we have an age function which assigns, which returns 15 in every case. And the program is asking the user, what is your age? And then we always get 15. Now, the problem is that you could match 1 to 12 inclusive, but then what age, but then what age would the child be? Instead, bind n for the sequence of 1 to n, and now the n, the age can be reported. That is the the issue is that we have a problem with rebinding. Age is a function. Its value only gets evaluated once. So often you won't have a problem because you might assign a variable early and then match on the variable. But here we are calling the function directly. And we want to go and use that variable type in multiple places and make a decision earlier. Let's find out what happens if we just use guards. How about we don't? I feel like I should follow on with the book. You can also use binding to destructure enum variants, and in our case, we have a some number, and that was sort of equivalent to age, and age returns, or some number returns a number, and match if its value, which has been bound to n, is equal to 42. And now we can use it in the scope. Let's just see the difference. So the tricky thing is here with copy types, you there is very little difference. And but this at symbol is available if you get into really into trouble with binding. It turns out that integers have slightly special behavior. They implement a trait called copy, and so they have different semantics than most user-defined types, and therefore it's not quite as this at symbol sequence isn't quite as applicable there. This is a really good one. I've got an optional value, which is a sum, but when we only need, and I could go and match on everything, and I've got lots of syntax, and I might have a none here. Instead, I can use if let sum equals, and then there's also an else, but it's not commonly used. And so now I've got access. I've got a destructured number, which is available to 7. I'm there. I've got access to 7. If you need to specify failure, use an else. And it's an else block. So, or it's a series of if statements. So if you wanted to, you could also have as many if else's as you needed. But by that point, you may as well have just used match. So it's very rare to see used in conjunction with if let. The fastest way to match on one specific variant is with if let. It doesn't actually need to bind a variable, which feels slightly odd. But what we're saying here is that if it, what we're sort of saying is that if A matches, let's say we had matches foobar, or if we had equals. Now, equals is different. Equals is implemented with a trait. So I could derive partial equality. Turns out, for reasons of floating point numbers that have to deal with not a number variance, that the equals operator relates to the partial equality trait. It's possible now to use the equals symbol, but the if let syntax is available out of sort of by default without having to implement any traits. It has a really rich ability to assign and destructure different items or inside it and provide access in a really elegant way to different parts of the type. So let me read this paragraph. Another benefit is that iflet allows us to match on non-parameterized enum variants. This is true even in cases where the enum doesn't implement or derive partial equality, which is what we just did. In such cases, if foo bar equals a would fail to compile because instances of cannot be equated. However, if let will continue to work. Would you like a challenge? Fix the following example to use if let. This enum neither implements nor derives partial equality. That's why you can't use double equals. So if let ta-da, let else. So this is quite recent Rust. With let else, a refutable pattern can match and bind variables in the surrounding scope like a normal get, or else diverge, which essentially means return, when the pattern doesn't match. So this is a lot of confusing sort of syntax, but we are using the from stir trait, which is about converting from a string into some actual data type. And it does this by, we start with some string s, oh gosh, and then split on white space and let takes a pattern, in our case, two options called by that has a count and the contents. And if that doesn't happen, then panic. So the split returns an iterator. The iterator has a next method. Next returns an option. Now, the count stir is a string, and item is also a string. So these are both the same type. I don't like using the type name in a variable. I feel like, we have Rust for a reason, but okay. We've got shadowing. We can do that. That's fine. Count is now converted to a U64. And if the conversion fails, then panic with an error message. This is almost equivalent to, this is almost equivalent to calling unwrap or expect, except for the fact that I've also got access to very structured data and sophisticated pattern matching, which I didn't have with expect. If I call this, it doesn't produce any output because it doesn't fail. The scope of name binding is the main thing that differentiates match from if let else. And this was introduced partially because of a lot of boilerplate that would have needed to have happened otherwise. There's a variation on if let, which is while let, which will continue to loop until something returns true, and it's possible to do it over just one option. Often you'll see this being used with an iterator, because or something that produces a, a list of options. We're finally at functions. Look, I'm only 3.5 hours in. I, um, obviously my voice is wrecked. I chapter 9, I made it halfway through. What I might, in fact, essentially a third of the way through. What I might do is come back in a future stream, because obviously I completely undercooked. Like, no, I underestimated how much is in this, and I'm not gonna get I can't get myself all the way through all of this in half an hour. The only thing that I will say is that the that if in, and because of we finally understand what function if is a functions that are declared using the if-in keyword. Its arguments are type annotated just like variables, and if the function returns a value, the return type must be specified. They are function pointers. If-in keyword. So in global scope, this is just a function pointer, and it doesn't need to be at the end. Have a break and some tea. That's a good challenge. Unfortunately, I've actually already scheduled meetings for myself in the afternoon, and so I can't just keep going until I'm done. I can push on a little bit longer, Shell. And 1 o'clock in the afternoon, gosh. Okay, let's keep going. Let's find out how far we get. I might actually do this again, and like a more structured. Maybe we'll do this every couple of months. We'll just try and do it again. It's quite fun doing it live because everyone has their own questions. Yeah, yeah, I think this is a good point. I am going to wrap up and say thank you. It's been a real pleasure to introduce myself to you. I thoroughly encourage you to subscribe to my YouTube channel if you have enjoyed the stream. It's been a real pleasure to, there we go, to see you on live. And there you are, by the way, you're sort of watching yourself watching me. And I am definitely planning on getting through more of Rust and more of the language through this book and through other examples. And so have a lot of fun. Feel free to message me either directly, privately, or publicly. Leave a comment if that's the way you'd like to provide any more suggestions for other content. I'm going to go have a nice hot drink and see if I can rest my voice for the rest of the afternoon. And I will see you later. It's been such a it's been a really fun 3 hours or so with you, and I thank everyone so much for staying with me. It's been a real pleasure. Take care. Bye.